So we're looking at this messaging aspect of AWS, and messaging is it's a way of decoupling, uh, well, in our case, decoupling Lambda components from one another, but it could be used for decoupling monolith applications from one another as well. In fact, that's, as I said to you, that's where it originated back in those days, so to speak, the pre-serverless days. So there are a couple of messaging services available to us, and we're started looking at the one called SQS, which, well, if we just take the image, the first image in the top right, uh, as I said, it was originated back in the days when we had monolith applications that needed to communicate with one another, but they had no way of doing it. Often these monolith applications were owned by different organizations. So there was no kind of agreed protocol, if you like, between them. And that's why AWS introduced this SQS service to facilitate that. And in the language of SQS, we have producers and consumers. Producers are compute components that write messages to a queue. Consumers read those messages. We also said that the way a consumer works is that it kind of periodically polls SQS asking it, do you have any messages in the queue for me? It doesn't work the other way. SQS doesn't contact the consumer and say, I've got some messages for you. It's up to the consumer to initiate the interaction, if you like. So we can fast forward because we've covered all this already. So this is kind of where we left off the last day, the bare bones of how we set up an SQS queue and then have a consumer kind of linked to that queue. So we saw this the last time. This is how we kind of link the consumer with a queue when the consumer is a Lambda component. So I talked my way through that example. Um, and to when we illustrated it, we just sent a piece of text, something like this, hello world, or a string, sorry, we sent a string as our message. But normally messages are data structures, and more often than not, they're going to be JSON data structures. So uh, on this slide here, if we want to send this JSON structure, if we want to publish it into a queue and then have a Lambda process the message, well, if we're using the CLI to publish the message, okay, we just do it like this. That's okay. We can refer to the message using this kind of file protocol. That's all right. So that's going to write the message into our queue. On the consumer side, then, what the consumer sees inside in the event object, a Lambda consumer sees inside in the event object, and I'm showing it to you here, right? The body of a message has actually been serialized or stringified by SQS. So like here, when we publish a message to the queue and we're passing it the JSON structure, let's assume this file contains this JSON structure here. What SQS does is it serializes this, and that's what it actually stores in the queue. It doesn't store the native JSON structure at all. And that's why then when a consumer comes along and tries to read a message, what it actually gets is the serialized version of it. So the overriding point, as Ross, I'm trying to make here is that one of the first things you need to do in your Lambda consumer is to parse this string in order to convert it back into its JSON form or JS form, I suppose, and then process it. Yeah. So this is just an excerpt from our Lambda consumer, and the critical line is this one here, where I'm going JSON.parse, and I'm taking the body of the message. So JSON.parse, as you know, takes a stringified version, a serialized version of a JSON object, and returns that JSON object in its JavaScript form. So you need to remember that, and we'll see that a lot anyway. Okay, that's that. Now, if I go right back to one of the earlier slides, I think it's the very first one we had. Where do I mention it? Yeah, here I'm saying that SQS is a fully managed distributed queuing service. Now, we know fully managed means it's kind of a byword now for serverless. We don't actually have to. There are servers running behind the scenes. There are SQS servers running behind the scenes, but we don't have to configure them or boot them up or anything like that. That's okay. But when I say distributed here, what do I mean by distributed? Okay. And that's what I'm trying to get across in this slide down here. So, and I actually grabbed this image straight from the SQS documentation, even though it's an old image, and I'll explain why I'm saying it's old. It's certainly pre-Lambda and all that, but if we just focus on this part of it here first. So when you create an SQS queue, whether you do it from the management console or using the CDK framework or using CloudFormation, doesn't really matter. When you create or ask CloudFormation to create an SQS queue, um, what it actually does is it creates multiple copies of that queue within a region. It is region based now, but it will create multiple copies of it. And it'll scatter those copies across the different AZ zones within the AWS region. So each copy is running on a separate server, really. Okay. So it looks like here there's 1, 2, 3, 4, 5, 6, 7. There are 7 copies of our SQS queue, a single SQS queue being maintained by the SQS service. Now, when I say they're copies, they're not full copies though. They're only partial copies. And so what happens is when a producer writes a message to this queue, what SQS does is it just randomly selects a subset of these nodes, of these servers, randomly selects a subset of them and stores the message in that subset. So for example, if you take message A here, it's stored on this one. It's not stored here. It is stored here. It's not stored here, and so on. You could look through them yourselves, right? So every message is not copied onto each node. Therefore, each node is not a full copy of an SQS queue. Okay, so that's what happens on the write side when you write a message or publish a message onto a queue. That's kind of straightforward enough. Now, when a consumer then, and this is our consumer on the left now, this is a reflection of how old this image is because we have 3 consumers here. Just kind of conveniently ignore that for now. Let's say our consumer is just a Lambda. So there's only one Lambda. Let's supposing this is it here, and we can forget about the other 2. And we know the way Lambda, if Lambda is a consumer, we know the way it works. It's actually the Lambda service polls SQS. So that's okay. So either way, our consumer polls SQS asking it for messages from the queue. Now, what SQS does is, again, it randomly selects a subset of its copies. So let's say the ones that are grayed out are the subset that it has selected for a particular instance of a polling. So it selected this one, and this one. And it asks, SQS asks each of the servers give me a batch of messages from your queue. And so they do respond back to SQS. Now, clearly, this one is going to have message A and this one is going to have message A as well. So SQS will perform deduplication. So it won't have two copies of message A in the response that it eventually sends back. It will perform deduplication in this case, right? You may or may not remember when I started talking about SQS 2 or 3 lectures ago, one of the caveats I mentioned was that there is a possibility of uh, duplicate copies of a message being returned to the consumer. Well, that's got nothing to do with what I'm describing here now. Okay, that duplicate copies relates more to the what's called the kind of eventual consistency part of SQS, which I'm not going to get into today. But so for this normal kind of consumption operation, SQS will perform deduplication. It will remove any duplicates. So it certainly won't, like there's only one instance of A, C, D, and B. Okay. And as well, okay, so it will perform deduplication. It won't perform any kind of ordering of the message because SQS doesn't know anything about the internals of the message. It wouldn't know how to put them in the right order. So the order that they appear in here is simply down to, which of the servers that it has selected comes back first with its response. They're all going to come back with a response, and SQS will perform deduplication because every message that's written to a queue gets its own unique identifier. So that's how it knows how to perform deduplication. And so it does perform deduplication, and then eventually it returns what's left back to the consumer. So the point I'm trying to really get across here is this idea of having multiple copies of the queue scattered across different AZ zones within the region that this queue has been created in. Like you can see that the heading for this slide is SQS is highly available. So if SQS selects this one, and this one, and let's say this server happens to be down, well, then it'll just take these two, whatever it gets back from these two. So that's how SQS kind of really works behind the scenes. Do we really need to know about that as developers? No, we don't really, but I think it's interesting to know how the AWS people decided to kind of honor this high availability, which is clearly something that we'd like. How it achieves high availability within the SQS service. Even though I said let's ignore it, like on the left here, we have three consumers. SQS allows for multiple consumers to be linked to the same queue. This really now goes back to pre-Lambda days and all that. And the way it worked, so if we have three consumers here, typically what these three consumers would be three instances of the same application that are running on separate servers. Yeah, that's kind of how we achieved scalability back in the early days. We have our monolithic application, and in order for that application to be able to deal with high volumes of traffic, we actually spun up a number of servers and installed the same application on each of the servers. Okay, so but they're separate applications really, certainly as far as SQS is concerned. It doesn't understand that the idea that these are three copies of the same. So strictly speaking, we have three consumers. And the way SQS works is if this one, let's say, if it polls SQS for some messages, and let's say this is the response, and it gives those messages to this consumer here, and it successfully processes each of those messages, okay, and then it tells it you can delete those messages now. Well, we can be guaranteed that these two other consumers will never see those messages. Okay, so it's kind of a first come, first served. That's the way SQS works. And again, that's all kind of irrelevant to us because we very rarely have this kind of scenario now. We just have one lambda. We'd rarely have two lambdas, two separate lambdas that are both consuming from the same queue. I suppose technically you can do it, but I can't think of a realistic scenario where, and the assumption is that the lambdas are performing slightly different processing. So anyway, that's kind of beside the point. The real point I want to get across is what's going on over here. Yeah, there's some detail then down here. Okay, I think that's just some reminder of what I've been saying over here. Okay, so that's nice to know, but doesn't really affect us as developers. Now, uh, in our case anyway, the consumer is nearly always a lambda, and we know that the lambda service does the polling of the SQS service, asking it for a batch of messages from the particular queue, and the SQS service responds with a batch of messages to our lambda. Now, and a batch is never going to have more than 10 messages in it, okay? Just by the way. But what the Lambda service does is it actually spins up a number of copies, yeah, of the micro VM and loads each of those micro VMs with our Lambda function. And it takes the batch of messages and splits it up and passes a subset of the overall batch to each of these Lambda instances. Now, by default, it nearly always spins up 5, but you can control it. You can say have no more than 3 or no more than 2. But if you don't tell it, then it will nearly always, sometimes not, but in most cases, it will spin up 5 lambdas. Now, these 5 lambdas here now, they are very different from what I was talking about over here. Sorry now about the toing and froing, but um, the whole point of the Lambda service spinning up 5 or at least multiple Lambda instances, all running the exact same Lambda function, is to deal with scalability, right? Rather than just spinning up one micro VM and loading that micro VM with our Lambda function, and then giving the entire batch of 10 messages, let's say, to that one Lambda, and let it work its way through it. Well, from a scalability point of view, if it spins up multiple Lambda instances, takes the batch of messages, breaks that batch up into sub batches, and gives a sub batch to each Lambda, and let each Lambda process the sub batch it has received. Clearly, from a scalability point of view, we get better performance. So again, you kind of get that for free. Um, Um, okay, so it does that behind the scenes. Now, if while these lambdas are processing the sub batches, while that's happening, the lambda service polls SQS again, and it gets another batch of 10 messages, and these lambdas are still busy, then it'll just spin up some more micro VMs, split the batch and distribute it towards the new set of micro VMs. And on and on it goes. So it'll keep on scaling up. Now, there is an upper limit. It'll never go above 1,000 uh, micro VMs all running the same. And you can throttle that if you want to. You can set it to a lower limit than that. But that's all happening outside of your control to a degree anyway. Um, Down here, I kind of am documenting the rate at which it's, what do I say? Uh, Do I give the action? Yeah, it adds up to 60 micro VMs per minute, up to a maximum of 1,000. So that's the kind of rate of scaling that it will do, and that's kind of built into the Lambda service. And it's all about scalability because when we move into a serverless world, we lose a certain amount of control. So we can't really control the scalability ish anyway. We've a certain amount, but we don't certainly have as much control over scalability than if we were using EC2s as our main compute component as opposed to Lambdas. Okay, so we can illustrate. I try to come up with an example which would prove that this is actually happening behind the scenes. And so here's the little demo that we're going to look at. Now I've got a Lambda here. This Lambda is actually going to be used to generate messages. Up to now, we've generated messages from the AWS CLI, but I wouldn't be able to generate messages quickly enough to prove the what's on the previous slide. So instead, I just wrote a Lambda as a kind of a test harness. So this Lambda creates, in my case, it just creates 10 messages, and it just sends those 10 messages almost in bulk to the SQS service. And on the other side, then we have our consumer. So what we'll notice is that the Lambda service will spin up a number of instances of our consumer Lambda when it receives a batch of messages from SQS. Yeah. Now, this Lambda, it does need to get permissions to write to SQS. I talked the last day, I spoke to you about the fact that this Lambda over here doesn't need direct permissions to talk to SQS because it doesn't talk to it directly. The Lambda service does. However, this Lambda over here, it does need permissions to write messages to the queue. But that's just a one-liner. It's a bit like giving a Lambda permission to write to a database. It's the same kind of idea. Here are some excerpts from this little case study. So I have defined some data types for myself. So the messages are Maria orders, customer orders, right? So here's an order, the structure of an order, customer name, address, and an array of items. Okay. Now I have defined some other types as well that aren't relevant to this demo. They will be relevant later on. So I've defined a bad order data type as well, where I'm making all of these things optional. Remember the partial utility type that we get in TypeScript. Don't really need to, we're not using it today though. And then I've defined another type called unvalidated order. An unvalidated order could be an order or a bad order. We're not going to be using this either today. This is just a piece of code that I'm going to use in my order generator Lambda. I've just got it's just a standard for loop, right? It's a for loop that's essentially it's generating an array of these structures. That's all that's going on here. And in each order, I make the customer name, I hard code it to user, and then a kind of a subscript number. So it'll be user 0, user 1, user 2, all the way up to user 9, I guess, because I'm going from 0 up to 9. So that's fine. So this piece of code, that's going to be inside in this Lambda here. And then this is how my Lambda writes messages. There's two ways you can write messages to a queue when you're using Lambdas. You can write them individually, or you can write them as a batch. If you write them as a batch, though, there can't be more than 10 messages in the batch. So this number 10 kind of seems to be ingrained within the SQS service, right? So that's why rather than this for loop here going from 0 to 20 or 0 to 50, that's why I actually went from 0 to 10. So I could actually write all of my messages as one batch to SQS. And I'm getting a reference to an SQS client. This looks very like, when we were talking to DynamoDB. So that's my SQS client. Um, SQS, the SQS SDK, its design is the exact same as all the other SDKs in the sense that we have these kind of command objects and we send a command object to our servers. So in this case, the command object is send message back, send message batch, sorry, request. That's our command. And essentially, each message has to have a message ID. So what I'm doing here is I'm generating my messages. And there are only two parts to a message. A message has an ID and the message body. The message body is going to be one of these guys over here. The message ID is I'm just using a package that generates a unique ID for me. Okay, this V4 package, just a JavaScript library. So, yeah, because you can see what I'm doing here is where is it? I'm mapping over my orders array. So I'm finishing up with an array of messages. And then I send to my SQS client, I send it this command which contains my batch of messages. Okay, so there's nothing terribly interesting there, right? That's just how I write to SQS. Um, this is on the consumer side then. So this what we're looking at here now is this Lambda on the right. And again, there's no surprise there, right? What is it doing? It's digging into the event object that it gets from the Lambda service. Sorry, now where is it? Uh, yeah, it's picking out the records property within the event object, and we saw that the last day. The records property contains our array of messages. It iterates over them, and for each one, it now has what we call a record, but a record really is one message. And I parse it, which I talked about at the beginning of the lecture. I do check to make sure it's a valid order. If it's not, it throws an exception. That will become relevant now in the next lecture, not today's lecture. Like what happens when a consumer actually throws an exception in the middle of processing a batch. Okay, there is a mechanism for dealing with that, but we needn't worry about it today because our array of orders were all valid ones. And then we process the order and we keep going in our loop. So that's straightforward enough. If I jump over the VS Code and quickly look at the stack file. So I have my queue. I have my Lambda, that's the consumer, process the orders. Again, just to reiterate, we don't have to pass a reference to the queue as an environment variable to this guy at all. I talked about that the last day. Here's the Lambda that generates the orders and writes messages to the queue. This time we do actually have to give it a reference to the queue as an environment variable because it's talking to it directly. Well, it's talking to SQS. Yeah. And this is how we make our consumer, how we make the queue the trigger for our consumer. We talked about that the last day, so there's nothing new there. This is how we give the producer permissions to write to the queue. Okay, so it's just a nice convenience function that's available to us from the CDK. Okay, grant send, what is it? Grant send messages. Okay, so that effectively attaches a policy to our producer, and the policy will say this Lambda can actually send messages to our SQS queue. And I'm outputting the producer's the producer Lambda. I'm outputting its name because we'll trigger this Lambda from the AWS CLI. That's how we kind of kickstart the whole thing. And these are the lambdas then, which I kind of looked at from the slides. So if I now try and trigger, so I deployed this earlier on, and if I now try and trigger the producer lambda, okay, so this is how I'm going to do it. AWS lambda invoke. This is the name for the generator lambda. Okay, so I'll just do that. Don't worry about that question there. That's just related to my CLI. And so it's running. And the delay there was because it generates 10 messages. Okay, so if I now flip over to uh, CloudWatch, and if I do a refresh here, notice I'm only getting one logs group. There should be two log groups, but I'm only getting one. Now that's because, and the log group that I'm getting here is the log group for the producer. I'm not getting the log group for the consumer. And the reason for that is there's a bit of a delay because my Lambda service is going to be polling the SQS. And well, we can control the frequency of the polling, but it certainly hasn't polled it straight away. So that's when I did a refresh there of my log groups. I only get one. Now, if I do it again, I'll certainly get two of them because while I was talking, the Lambda service will have polled SQS. And there we go. Now, we don't really care about the producer, the generate orders. This is the one we're interested in. So this is the log group for the consumer, right? And lo and behold, wow, there's too many streams there now. Let's see, 1346. These 1240 ones now are older ones actually. They're ones that I ran earlier. So it's the 1346 ones are the one we're interested in. They're the ones that ran just at 1348. But, and there's one, two, three, four, five. Yeah, there are five of them. So what does that tell me? That tells me that there were five micro VM instances spun up by the Lambda service. Each of them was loaded with the consumer Lambda. The Lambda service split the batch of messages that it got from SQS and distributed those batches across each of these micro VM instances. And so if we just select one of them, let's take the first one. Uh, and what I can tell from this one is that it actually got a batch that consisted of only one message. Like I send in 10 messages, right? It doesn't when the Lambda service polled SQS and it got the 10 messages back in the response from SQS. And I said it splits that batch up into sub batches. It doesn't necessarily split it up into even sub batches, uh, right? And we can kind of, and this is confirmation of it because it looks like one of the sub batches only contains one message, and it was the message for customer three, user three. Let's look at another batch or another log stream. This one. Similar kind of stuff here, actually. This is for user seven. It's kind of odd now, that's okay. So it only got one message from the batch as well. Let's look at the third stream. One of the streams now will have gotten quite a lot of messages, and this one has got quite a lot of them. So it's got a batch for order 8, order 9, and order 2. And so I think by my calculations, maybe the last one. I don't know how many we've looked at now. We've only looked at three actually, yeah. This is four, fourth one. It got some other ones. It got user four order, user five, user zero. So, you know, hopefully I've kind of demonstrated to you that the Lambda service did actually perform scaling when it got a batch of 10 messages from SQS when it polled it. And, it scaled up to five instances, which is kind of the default. And sometimes one of those, or maybe probably not more than one, but often one of those instances receives a batch with nothing in it, so it kind of overdid it really in terms of scaling up. But okay, so I've kind of shown you hopefully that the Lambda service does perform scaling. The other thing we can see if we just look at this one here, right, is that there's no there's no ordering of the messages. So let's say for this one here, we got the order four, five, and the first one we started at zero, wasn't it? Yeah. So this is really order one. This is order four. This is order three. But they're not necessarily in the right order or in the right sequence. Yeah. And you have to accept that. You can configure your SQSQ such that the ordering of the message is preserved, but that actually impacts on performance. And you kind of have to tell SQS what property of the message should it use to determine the ordering of messages. Right. So that's back to my slides. It's kind of showing you this where did I have it? Sorry. This scaling working for us. I can just do one other actually tweaking of that. If I go back to CloudWatch and if I do a cleanup, let's delete everything. Although, sorry, even though we tell it to delete log messages, as you saw there were log messages from an old invocation still hanging around, even though I would have deleted them before the lecture. But if I just go back to my code, there is a setting that you can, let's see, where is it? There's a configuration setting that you can use to control the degree of scaling up, which is this one here. So there's this max concurrency property. Now, if you don't set it, it defaults to five, but you can set it something, you cannot set it to one, but it's something above that. So if we set it to two, let's say, which is really the lowest actually that you can set it to, but let's do that. Now, what that will mean is that um, the Lambda service will never scale up its consumer by more than two concurrent instances, right? Let's set it to three actually. And if I redeploy, and I'm going to trigger the producer Lambda again, but this time we find that there will only be three log streams for my consumer Lambda. There certainly won't be five. There may be only two, but there certainly won't be more than three. So we let the deployment run to completion. And it's the same Lambda, so I can trigger it again. So again, I'm sending a batch of 10 messages into my queue via the producer Lambda. Back to CloudWatch. Do a refresh. Again, there's a bit of a delay before I get to see the consumer Lambda. Still delayed. Still hasn't done the polling. No, still hasn't polled. And eventually it has polled it. And if I go into the log streams, now again it's holding on to the old ones, but we can tell from the timestamp. So 13:57. So there's one, two, three, and there's only three. Yeah, which is exactly what we said. Don't scale it up by more than three concurrent instances. And if we look through, uh, well, let's not go through it all now again. But so this one got order number 9, which was user 8 because we started 0, and order number 6 again. Like they're not in they're not in the correct sequence, and that was it. If we actually look at the event object itself. Here's my records property of my event object, and that contains an array. And so here's my array here. And the array will contain two messages because I've just shown that it actually received two messages. So the first message begins here. Here's the body of the message. And if you look closely at it, it will be for user 8. And here's the second message. And again, the body of it tells it it was for user 6. So that kind of all tallies up. Yeah. Okay, so we have it. We can control the upper limit of the concurrency. If that's because we're we're paying for every Lambda instance that it spins up. So that's fine. That's that. They're just screenshots really from what I've been showing you, so I don't need to talk through them, I think. Oh yeah, and that's just the max concurrency setting that I was just talking about. So we've covered that. Um, so there's this thing called message visibility. How are we doing on time? Um, and so the idea here is that when a consumer, and to date now, Lambda has been our only consumer, but there can be other consumers as well. When a consumer polls SQS, asking it for a batch of messages, and SQS responds and returns a batch back to the consumer. Uh, I did mention to you that it's the responsibility of the consumer when it has successfully processed that batch. It's the responsibility of the consumer to ask SQS to delete those messages so that no other consumer will receive them. Okay. Now we never see any of that evident in our code because the way the Lambda service works is it takes care of handling that kind of cleanup for us. We don't have to program it in our Lambda functions, which is kind of neat. But going back to the polling, so the consumer polls SQS and SQS responds with a batch of messages. Now it leaves those messages in its queue though. It doesn't delete them, but what it does is it sets a kind of a flag in those messages, and this is called the kind of visibility flag. Uh, and by setting this flag, no other consumer can see those messages because while the first consumer is processing the batch of messages that it receives, another consumer might come along and request SQS for a batch of messages, and that other consumer should not receive any of the messages that it sent to the first consumer. And so the way SQS ensures that is that it makes sure that it doesn't give to the second consumer, it doesn't give it any message that has this visibility kind of Boolean already set. Yeah. So it sets this visibility property to ensure that no other consumer sees a message that it has already provided to the first consumer. Now, of course, it doesn't let a message be invisible forever. If the first consumer, for whatever reason, doesn't come back and ask it to delete the batch of messages because it hasn't processed them successfully, then SQS in that case will disable this visibility property, thus making the message visible again. So there's a time limit on this visibility property. And if the first consumer does not ask SQS to delete the message within the time limit, then SQS will automatically make that message visible again and available to the next time somebody consumes it. Could be the same consumer. It doesn't make any distinction between it. So that's again, that's what kind of what's happening behind the scenes. So when a message is polled by a consumer, it remains in the queue, but it's invisible. It's invisible to other consumers by this property. The default message visibility. Okay, so there's a visibility timeout period, and we can configure that. So again, I mean, it depends from application to application as to how long it takes a consumer to process a message, right? So that's a kind of a fine-tuning aspect of any application. But the default, it seems, is 30 seconds. But as I said, we can configure that in our code. The consumer must process and delete the messages within this timeout, otherwise the message will become visible again. And the kind of the graphic illustrates what we're trying to get across here. In real life production applications, setting the visibility timeout period for particular queues, that would be important, all right. Because clearly, like I'm saying down here, if you set the visibility timeout to be too long, you set it in terms of minutes or even hours, depending on the nature of the message. If it's set too long, then that means messages will remain invisible in a queue for too long a period and they're not being processed quickly enough in an overall sense. If you set the visibility too short, though, then you're increasing the possibility that the same message will be processed more than once. So it's a fine-tuning thing, setting this visibility timeout period on a queue by queue basis. In fact, if we go back to uh, the lib file, you can see there that it's actually a property of the queue that you can configure. We're not going to get into it though, but again, it's something that's worthwhile knowing about in the background. Okay, I am going to stop at this stage and we'll deal with this idea of dead letter queues the next day. What dead letter queues are all about is, well, what if one of your consumer lambdas, in our case, throws an exception when it's processing a batch of messages? How do we, because we need to be able to deal with that eventuality will arise. So we need to have a way of dealing with it. And the SQS service provides us with a mechanism for dealing with that, which is this dead letter queue facility. Right. I'm going to stop at that for today. Uh, as usual, I'll just allow questions in case there are any questions. No?
Can I ask one thing, but it's not regarding this one, it's more with the assignment.
Okay.
Is the I'm almost done just with the domain, and I don't know if we should buy it, like buy the domain and or like
Yeah, that there is a cost involved in it, I know. Uh, but I don't think it's expensive though, is it?
it's not it's like I think it's I checked it, it was I think less than $5.
Who did
So
you, what service did you go to? What registry did you go to?
uh I think I was looking up how much does it cost because I know buying a domain like sorry put what's that called, getting a domain requires like paying and buying it, and
Yeah,
I just looked up how much it costs, and I think couldn't remember when I looked it up, but I think it was like $5 something like that.
that sounds
And
about right.
it's yeah, but then I don't know if we like it's like oh because it's not much, but just like I don't know if it's like we just need to demonstrate that we can do this or uh like
There's no, see, the problem is there's no way of demonstrating it without buying it.
yeah that is
And
true.
the only reason I left that in the spec was because I didn't think it was expensive. If it was going to be $100, then I wouldn't have included it in the spec. I'd have come up with something else.
Yeah, that makes sense. That is
Yeah.
it's not much. I just want to make sure that, and also for the domain, it's just on the client, the front end side. Is it or do we need to do the custom domain for the API, like the
No,
uh,
no, you're
like
buying.
gateway?
Well, I mean, when you buy a domain, you can split up into subdomains. So technically, you could have one subdomain for the API and another subdomain for the front end. I'm not asking you to do that though. I'm
Okay,
just asking you to link a subdomain of your main domain to your front end.
so just the front end only.
Yeah.
Yeah, okay, that
Yeah,
makes sense.
that's all I've demonstrated in the sample project that I gave you.
Yeah,
I don't think it would be. You just need another Route 53 record.
yeah.
I'd imagine another Route 53 record to link the API with its own subdomain. But you don't have to do that. Yeah,
Okay.
yeah,
That
yeah.
makes sense. Because I was just gonna, because I know we can do both, but because when you say the domain, it's more of just for the front end, but I don't know if I should also do it for the API gateway as well.
No,
And that, yeah, that makes sense.
you,
Just
you you can if you want to, but it's not in the spec, so it would come under other. I'm not sure if I included other in the spec, but um, no, let's predominantly it's the for the front end, subdomain for the front
yeah,
end.
yeah, that's very good right now.
Yep, that's great. Okay, we leave it at that. Thanks. Bye bye.
Thank you.